Hello everyone, welcome back to my channel. Since the introduction of ChatGPT last year, the large language models research has drawn a lot of attention. In this field, there is a recent very influential technique called chain of thought prompting. So the core idea of this method is basically that we human beings show the machine several examples, not only the answer, but also the chain of thought process and how we arrive the answers. And the machines are expected to mimic the behavior of us human beings. And then on a given question, it is expected to not only arrive the final answer, but also firstly decompose the complicated problems into several sub-steps and display the thinking process in front of us human beings. So how does this technique work and what's the limitation of it? So today, let's have a look. But before that, I want to give a brief introduction about large language models. What's the learning paradigm of it? So for those people who just recently got into the field or then unfamiliar with it, then it's a good chance to kind of have an overview of the entire context before diving into the technique. Okay, so let's get started. So large language models basically refer to a class of neural network language models that are of large scale. Typically, the architecture is transformers, and the scale of the parameters is kind of like billions of parameters, tens of billions of parameters, hundreds of billions of parameters. So it's kind of very large scale. The model is very large scale. The training data is also typically a very large training data set. But when we actually refer to large language models at the moment, we typically refer to a training paradigm, a learning paradigm. So how does that actually work? Let's briefly look at it. So large language models, we have a model that is particularly large scale. And the first step we want to do is kind of, we want to train it on a large data set. So that's kind of called the pre-training process. Typically, this data set contains enriched semantic information and a lot of knowledge about the real world. For example, the ideal situation is that you can collect all of the information from the internet, and that's kind of very large scale and contains different perspectives of information. And later on, it's crucial that the machine can utilize some pre-trained knowledge to kind of solve some unseen tasks, okay? And the second step is to actually do few-shot learning. So the few-shot learning here is a little bit different from the context of computer vision. So in computer vision, a few-shot learning typically means that you fine-tune the model, typically involves some new optimization process such as gradient descent or whatever. You fine-tune the model on kind of some examples of the new data set or the downstream task-related data set. But here, it's more often refers to a kind of a new learning paradigm, which is generally called in-context learning. So the spotlight of it is that although it's called learning, but it does not involve any optimization process. So here, something is involved, which is called prompts. So suppose that we want the machine to be able to do Q&A task, then what we do at inference time, so here, this is downstream task related, okay? And this happens during the inference time, when we actually want to utilize the pre-trained model to do actually something useful for the downstream task specifically. So the format of the prompts look like this. So give an example of question 1, and we also give the associated answer, which is called A1. We give another example Q2, and we give another associated answer, which is called A2, okay? And suddenly, when we have some input-output label pairs, and suddenly we have a new question, which is called Q3, and then we let the machine infer what the answer is going to be in this situation. So, so the first two examples, although they're kind of new training examples, but we actually condition on them when doing inference, when asking the machine to do inference, rather than actually tuning any parameters directly with it. So what we do is that we typically condition on this entire whole thing and ask machine to generate the final answer A3 for us. So this is kind of a learning paradigm on how people utilize pre-trained models, pre-trained large language models to actually finish downstream related tasks. So it has a lot of research on, first of all, how to make the prompts better such that the machine learning model or the language model can actually achieve better performance in downstream tasks. So this is a large class of work called prompt engineering. So for example, the order of the prompts can affect the model performance, okay, and the format of the prompts, etc., etc. And there is another category of work, which is that why does in-context learning actually work? So you do no gradient descent, but it kind of magically learns to mimic the behavior on the given input and output label pairs. So how does it actually work? So you just do some conditioning, and then it will try to predict the unseen question, mimicking the behavior of the previous examples given by us human beings. So how does it actually work? It kind of seems like a magic, right? We don't really do direct optimization. So there are a few works, or it's actually a very active research area. A lot of people are actually researching on this perspective. So there are a few works. For example, there is a paper from Microsoft, Peking University, Tsinghua University. They kind of view this in-context learning as a meta-optimization process. So it's not explicit gradient descent process, but it's kind of a more like a meta level, okay? So meta-optimization perspective. And another very popular way to actually look at it is kind of an implicit Bayesian inference. So this work is actually from Stanford University. So there are also other works that actively investigate why does in-context learning work, what's the underlying mechanism of it. Okay, so again, the point is that there is no gradient descent, no optimization directly to tune the parameters, but we just condition on the given prompts, and then the machine magically can learn to predict the unseen example. Okay, so that's the basic background we need to know in order to understand the paper we are going to discuss today. Okay, so now let's officially step into the paper. Let's officially look at the paper. So the first paragraph of the abstract is basically they give a brief introduction about the chain of thought methodology. So is a series of intermediate reasoning steps significantly improves the ability of large language models to perform complex reasoning tasks. And in particular, we show how such reasoning abilities emerge naturally in sufficiently large language models via a simple method called chain of thought prompting. Okay, so notice their wording here. So how such reasoning abilities emerge naturally in sufficiently large language models. So on the other hand, it basically means that it does not perform so well in kind of small scale models. Okay, and in the second paragraph, they briefly mentioned that, okay, our technique has amazing or stunning performance. They mentioned that experiments on 3 large language models show that chain of thought prompting improves performance on a range of arithmetic, common sense, and symbolic reasoning tasks. I have to say that their experiments are pretty complete and broad. So this is kind of persuasive perspective, that also gain benefits in their paper review process. So the empirical gains can be striking. For instance, prompting a Google pathway model with 540 billion parameters with just 8 chain of thought exemplars achieves state-of-the-art accuracy on the arithmetic reasoning dataset benchmark, surpassing even the fine-tuned GPT-3 model. Okay, it's quite interesting. You may be attracted by the abstract of the paper, but actually, as we can see later on, this paper also has several limitations, and they discuss this frankly in their analysis or like discussion part of this paper. Okay, so one very good benefit of this paper is that they have an illustration figure in the very first page of their paper. So this is typically beneficial if you want the reviewer or the reader to have a general idea of what is your core innovation of this paper, what is your core technique of this paper before they actually diving into the text. Okay, and this is also beneficial that if you want to increase the leverage of your paper. Okay, so if people have an easier time, understanding your methodology, then it means that your paper will get a faster spread across the community. So here, this paper is very clear, and the methodology, as we can see, is also very straightforward. So let's have a quick look. So they compare the standard prompting technique with the chain of thought prompting technique. So in the standard prompting technique, in the prompts, they have a question, they have an answer. So this is kind of demonstration input-output label pair, okay? And they have a new question, and the model is expected to provide answer for that new question based on conditioned on the new question, as well as the demonstration input-output label pairs, okay? So in this case, for a specific question, Roger has 5 tennis balls. He buys 2 more cans of tennis balls. Each can has 3 tennis balls. How many tennis balls does he end up with? So the answer is 11. Like, it's actually a final answer, okay, with no intermediate thinking process. In this case, as we can all see, that the model actually gives a wrong answer, 27. Okay? So in comparison, let's look at what chain of thought prompting does in this case. So instead of directly giving an answer in the prompts, in the input prompts, what the answer actually shows is that Roger started with 5 balls. 2 cans of 3 tennis balls each is a total of 6 tennis balls. So if you just aggregate the 2 parts together, originally Roger has 5 balls. Now he has 6 additional balls. Then at the very end, he end up with 11 balls in total. Okay, so the final answer is 11. So it's a complete thinking process. There are intermediate steps of this calculation, very clear how the examples arrive at this answer. And it turns out that this kind of answer demonstration here is annotated by human beings, okay? So we human beings directly show the machine that at inference time, you should have some intermediate steps and conclusions before you actually reach the final conclusion. So in this case, that the model just mimics behavior in the demonstration pairs, and say like the cafeteria had 23 apples. If they use 20 to make lunch and bought 6 more, how many apples do they have? Okay, so in this case, that the model mimics the behavior of the chain of thought process. So the cafeteria originally had 23 apples, and they use 20 to do something, and then they have 3 at the moment, but they actually bought 6 more apples, which ends up 9 apples in total at the very end. So the final answer is 9. Okay, so as a comparison, the left-hand side, the model arrives at final answer of 27 with no reasoning. It's the wrong answer. People don't understand what is going on there. What's intermediate steps are wrong. But here, the models not only predicts the final answer, but also gives a very thorough thinking process or intermediate steps before arriving at the final answer. So this is a kind of benefit as mentioned by the authors, which is treated as one of the major contributions of this paper, which is that a chain of thought provides an interpretable window into the behavior of the model, okay, suggesting how it might have arrived at a particular answer and providing opportunities to actually debug where the reasoning path went wrong. Okay, so this is a very useful aspect. I think it's even more meaningful or more kind of valuable than the technique itself, compared to the stunning performance itself. This interpretation is itself very, very important. Okay, and this actually leads me to recall one aspect of explainable AI. So in the domain of explainable deep learning, there is a subfield called basically utilizing natural language explanations to explain the decision-making mechanism of the machines. If you're interested about that kind of work, then basically you can go and search related papers, okay? Okay, so that's pretty much it about the core idea. That's pretty much it about the core idea of this paper. So as the authors mentioned, they do a lot of experiments to test or validate their technology. So there are 3 parts of it, which is arithmetic reasoning, okay? There is also common sense reasoning, and as the last step, there is symbolic reasoning, okay? So let's first of all have a look at the arithmetic reasoning part of the paper, okay? So they test, a few different benchmark data sets, okay? And they compare chain of thought prompting with the standard prompting technique, okay? They used different language models here, the GPT-3 model, Lambda model, Google Pathway language model, UL2 20 billion parameter model, as well as the Codex model from OpenAI. Okay, it's a relatively complete site. Okay, they have a graph here illustrating their performance compared to the baseline standard prompting technique. So I guess there are 2 major conclusions that we can draw from this illustration figure here, or the result figure here, okay? So the x-axis they adopted is actually the model scale, okay? So if you increase the model scale, what's kind of the performance change? What's the performance change with respect to the chain of thought prompting technique and with respect to the standard prompting technique? So the first point we can see is that on some relatively smaller scale language model, Okay, for example, like Google Pathway Language Model, if you just adopt like 8 billion parameters there, chain of thought prompting turns out to be not super beneficial in this scenario. Okay, as we can see that performance similar or sometimes even worse than the standard prompting technique. Okay, but as the model scale just got increased, for some cases, the chain of thought prompting techniques just greatly outperform the baseline standard prompting technique here. So here, the performance is very stunning for the Google Pathway language model, as well as for the GPT model as well. On the GSM 8K dataset, if you just adopt their larger scale model, then basically that their technique chain of thought outperforms the standard prompting by a very large margin. Okay. As they mentioned in the paper, this is something called emergent ability. Okay, so Jason Wei et al. They have a paper which specifically describes the emergent abilities in large language models. Basically means that there are certain abilities that only appear in large enough language models. They do not appear in small scale language models, and chain of thought prompting is definitely one of it. Okay, so as we can see that as the scale of the model just increase and gets larger and larger, okay, its benefit in terms of model performance or task-related performance just got increased significantly. Okay, this is kind of the first conclusion that we can draw from this resulting figure. Okay, the second thing is that we kind of see a difference in terms of outperformance on different models and different data sets. For example, for the GPT model, okay, on these two different data sets, the performance is kind of, the performance gap between the two methods is quite different, right? Here, the GSM-8K data set, the performance gap is super large, but here it's relatively similar, okay? And this performance gap, the difference, this instability of this performance gap also, got reflected on different models, say the Lambda model, right? In the Lambda model, it doesn't ever show like that very stunning performance gap, okay, across different data sets. So we see that the chain of thought prompting, its performance really varies from data sets to data sets and from language models to language models. I think that's kind of problem. And they also, when they conducted ablation studies to kind of test the robustness of the model, they also mentioned this point. It's worth discussing, okay? So yeah, and I think one very valuable point of this paper is that it conducted a sufficient amount of ablation studies. First of all, they kind of test what is the actual effect that makes chain of thought prompting works. So there are two parts in the arithmetic reasoning tasks, right? There are intermediate mathematical equations. There are also intermediate natural language reasoning sentences. So which part actually matters more? So some people may argue that those natural language reasoning sentences don't affect as much as the mathematical equations. Okay, so they conducted this kind of ablation study to only include the mathematical equation, but as we have seen that it doesn't really improve much in terms of performance compared to the baseline method, which is a standard prompting, the yellow block there. Okay. The second point is that obviously that the chain of thought prompting involves a lot of more computation compared to the standard prompting? Is it just the computation just matters in terms of the final model performance? And in order to validate this point, they actually use a sequence of dots. I think it's relatively creative. They adopted a sequence of dots to actually increase the amount of computation used in the standard prompting techniques. And as a result shows, it doesn't really improve the final performance of the model, okay? And if the last question, the last perspective they have studied as a part of the ablation study is that they study the order between the chain of thought and answer, okay? Is it really necessary for the chain of thought to occur before the final answer? And obviously, as an observation, we can see, yes, we should always have the reasoning appear first and the final conclusion appear at the very end of the prediction, okay? So as we can see that in all of these three cases, it doesn't really improve upon the baseline very much. It achieves pretty similar performance, but the chain of thought prompting outperformed largely compared to all of those three variations. So this is a useful ablation study. I love it, okay? And another very useful point, very valuable point is that they conducted studies to validate the robustness of chain of thought, okay? So they mentioned that sensitivity to exemplars is a key consideration of prompting approaches. So sensitivity to exemplars, it could include several aspects. For example, the order of the exemplars, okay, the number of the exemplars, etc., etc. And as a complete review of the list, they actually have extra information included in the appendix of this paper. So as we can see that here in the 8.2 section of their appendix, they actually studied the role of prompt engineering in their work in the case of chain of thought prompting, okay? So they studied the effect of different annotators and annotators without machine learning background, different exemplars, different order of exemplars, and different number of exemplars, as well as different language models. Okay, it's a very useful study here. So as I have mentioned before, they actually have a section, have a paragraph to talk about the effect of different data sets and different language models. So they mentioned specifically that we find that with the same prompts, chain of thought prompting improves performance across all three models for all data sets except what and what for what model, okay? The fact that gains from chain of thought did not transfer perfectly among models is a limitation, okay? They directly mentioned this, okay? And further work could investigate how different pre-training data sets and model architectures affect. So why do they affect the performance gain from the chain of thought prompting technique? Okay, so they themselves are not clear, like under what specific tasks or under what specific pre-trained language model will chain of thought prompting work better, okay? But I really appreciate their pointing out this in their analysis part of this paper, okay? So they also mentioned that prompt engineering is still a matter, okay? There are potential, for example, automation techniques out there, but right now it's kind of like the work still kind of more or less rely on like prompt engineering a little bit, okay? Okay, so that's about their arithmetic reasoning part of their empirical work. And they also conducted experiments on common sense reasoning. They adopted various data sets, okay? And also, as we can see that, for example, on this data set, chain of thought prompting do not obtain that much gain compared to the standard prompting technique. But for some other data sets or tasks, for example, like in like the sparse data set, actually even for like smaller scale of models, like you see that 8 billion parameters Google Pathway model, the chain of thought prompting even largely outperformed the standard prompting technique. So it's kind of a mystery, right? Well, like in what situations chain of thought prompting really works. Okay, so like for data task, strategy QA task, when the model scale is actually large enough, chain of thought prompting also outperforms the standard prompting baseline by a large margin. Okay. So the next part is the symbolic reasoning analysis. So it's a little funny that they actually do some toy experiments. I think part of the reason is that this section is not their kind of their major work. Okay, so if you actually look at the task they're trying to solve, in that they're trying to concatenate the last letters of within a name. For example, Amy Brown. The task is just to retrieve the last letter of the first name and last name. So Y and N, and concatenated them together and get us a prediction, which is YN. Okay, I mean, this is a toy example because at this stage, we human beings should expect language models to do much more than that. Okay, if you look at the capability of ChatGPT, it definitely is able to solve much more complicated problems than this. So also coin flip examples. So yeah, I guess they just use it as kind of a toy example to kind of cover this perspective of symbolic reasoning, which is not the major work they are trying to conduct in this paper. Okay, so that's pretty much the major content of this paper. Another thing I want to discuss in particular is the limitation of this work. Okay, so the authors, they use a paragraph to discuss the limitations here at the end of section 6. So let's look at it and actually reflect on the disadvantages, potential disadvantages of this method. First of all, they qualify that although chain of thought emulates the thought process of human reasoners, but it's not clear, it's unclear to human beings that whether the machine actually understands the problem, they actually have the capability to reason, or they just mimic the behavior of the demonstrations there given by us human beings, right? It's unclear, okay? And in the short term, we probably won't have a clue on whether the machine is able to think, or it just kind of mimics the existing demonstrations in a superficial way. Okay. And the second point is that although the cost of manually augmenting exemplars with chains of thought is minimal in the few-shot setting, such annotation costs could be prohibitive for fine-tuning. Okay, so as we see that there were 3 annotators that were involved in generating the chain of thought demonstrations for the machine, okay, to mimic. So it involves like human labor work, and you know, there's associated cost of it. Okay, for example, in terms of the time spent on this human labor work. Okay. And third, there is no guarantee of correct reasoning paths for what should be a correct reasoning. For example, if you just solve a mathematics question, there is one final correct answer, but there could be different methodologies to actually solve it. So different methodologies could lead to the same correct answer. Okay, so it's kind of a question on what path should the machine follow? What path should be included in the demonstration pair to actually show the machines how to solve the problem? So it's kind of a open question to be discussed, to be thought about. And at the very last step, the emergence of chain thought reasoning only appear, okay, at large scale models. And this is costly to serve in real world applications, okay. So if you think about it, if you just want to utilize the existing pre-trained models, utilize their APIs to solve your task at hand, that's fine. But whenever you have some, for example, smaller scale models that you train from scratch on your, for example, specific task at hand, then it's very hard to actually utilize chain of thought prompting technique in the inference time and expect it to perform very well. Okay, so this is kind of I regard it as a major limitation of this work. So yeah, it's overall it's quite interesting work, and as we can see that there's acquires a lot of attention and has a lot of leverage within a short amount of time after the publication. So this is a still relatively new paper, but it already got more than 200 citations. So yeah, basically there are also later works that build on top of this work to solve other, say, like natural language tasks. So so yeah, I would strongly encourage you to have a look at related papers. For example, there is another paper by Google Research later on that solves quantitative reasoning tasks, which also like utilizes this kind of chain of thought prompting technique. And that paper kind of solves more complicated mathematical problems for example, the high school mathematics, but they also actually have larger or more related training data set, for example, like arXiv math papers. Okay, so quite interesting works. Thanks very much for watching this video.